So first speaker is Magee from Durham, Thermodynamical Formalism and Markoff-Hurwitz equations. Please.
Thank you very much for the introduction and the invitation to speak here. So what I want to talk about today is, starting with the problem in number theory, explain how you can use thermodynamical formalism and transfer operators to solve this problem. So let me set the stage for the talk. So we begin with some Diophantine equations. So the first I want to show you is x squared plus y squared plus z squared is 3xyz. I'm not sure whether I should say z or z here. I'm confused. So this Diophantine equation may be familiar. This was studied by Markoff in 1880. So this Diophantine equation appears in connection with Diophantine approximation of irrationals, in particular the Markov spectrum and Markov's theorem. It's also connected to character varieties, so varieties of SL2C local systems on a once punctured torus. Okay, so it's connected to number theory and geometry. So slightly later, Hurwitz also decided to study this type of equation, and he considered a generalization to more variables. So Hurwitz considered the equation x1 squared plus x2 squared. So he now has n variables. And instead of 3, we put an a. And then we multiply all the variables together here. So this is Hurwitz. So I'm not sure I can explain why Hurwitz decided to study this, but we're interested in integer solutions to these equations. So this equation arises from a fairly simple question, which is, when is the product of integers, when is the sum of squares of integers equal to a multiple of the product? Okay, so it's a very simple question. All right. And then the actual most general version of this type of equation I want to discuss was discussed by Mordell in his book on Diophantinegeometry. So this is published, I can't remember the year, it's the 1970s. And what Mordell does is he just adds an additive constant. So we have a, x1, xn. Okay. So this is what I'll talk about in the talk. So throughout the talk, n will be at least 3. A, I want to be a natural number, and I want k to be an integer. Please feel free to ask me any questions about what I'm doing if you want more motivation. At any point, if you want more motivation, ask me and I'll give it. Okay, so you have these Diophantine equations. This is part of Diophantinegeometry. Basically, if I write down a random Diophantine equation, you're going to have a really hard job to write down any solutions or explain to me how many solutions there are. Okay, so this is like a really hard area. There are very few cases of Diophantine equations where the integer solutions are understood. But this is actually one of them. Okay, so that's what the talk is about. So the main question for the talk is going to be, what is the size? Oh, okay, let me give this a name. I didn't leave enough space. So I'm going to call this thing V. So if you know what this means, you can think of I'm defining an algebraic variety. If you don't know what that means, V is the name of this equation. Okay? Okay, so I want to know what are the integer solutions to that equation, or the integer points on the variety. But I'm going to try to say how many are there. There are infinitely many. So if I want to actually have a counting problem, I have to intersect with something, okay? So I'm going to intersect with a ball. Okay, so throughout the entire talk, every ball is an L infinity. So what I'm saying here is control the maximum modulus of any entry, yeah? And I mean, take this is my notation for size. What is the size of this intersection? How many integer points are there in all the radius r? Okay, so that's the question. What is the size of this? Alright, so as I mentioned, Diophantine equations are hard, but this one is not as hard. So what's special about this Diophantine equation? The special thing about this Diophantine equation, which makes it interesting for us, is that this variety has an extremely large group of automorphisms. Okay. So, okay, let me take some space. And this is going to be a theorem. So it's a theorem of U. So what is an automorphism of the variety? I just mean something very simple. I mean a complex polynomial map of C to the n-dimensional complex vector space that preserves this polynomial. That's it. So it's actually known what the automorphisms are. So the theorem is that the automorphisms of this equation or variety. Okay, so I'm going to write it as an abstract group, and then I'm going to tell you how the abstract group is manifested as polynomials. Okay, so you have a large, an infinite part, which is, this is a cyclic group of size 2, and it's not just a cyclic group of size 2, it's the free product of a cyclic group of size 2 with itself n times. This is a group which is generated by a1 up to an, such that a1 squared equals 1, a2 squared equals 1, etc., and there are no other relations. Like, kind of like a free group, but generators are involutions. Alright, so this is the main part of it, but there's an extra part. So this is a semi-direct product with a finite group, which is, sorry, it's itself a semi-direct product of two finite groups. So this is, Sn is a permutation group on n letters. The way that acts is just permuting the coordinates. I have to reach. This is permutations of coordinates.
And sorry, n was what?
I'm about to tell you.
Ah,
So n is a abelian group. So what n does is also simple. You're just allowed to change the sign of an even number of the coordinates, right? So that will preserve all the squares, and it will also preserve this because you do an even number. So n is even sign changes.
so the C2 again, what was that again you say?
So as an abstract group, I just said what it was as an abstract group. I'm about to tell you what the generators are. Okay, so this is the most interesting part.
Yeah.
So the generators of the C2 to the star n are generated, this is generated by Markoff-Hurwitz. Which are also sometimes called Vieta involutions. Okay, so how do you get these? These are the non-trivial things, like the more interesting things. Okay, so we can just look at, okay, let's look at this. Okay, so this Diophantine equation has a certain property, which is that it's almost quadratic in every one variable if you fix the other ones. So you can do a Markov move at every variable, and the way you do that is you fix all the other ones. Yeah? So they're all fixed, like x2 up to xn are fixed. So we have a quadratic polynomial in x1. Okay, so okay, it has two roots. And then, okay, the reason it's called Vieta's involution is because you have something called Vieta's rule, which is that when you have a quadratic polynomial, the sum of the two roots is negative the linear coefficient. Right? That means that you can do root flipping if you only know the linear coefficient. So for example, let's flip the root of x1. So this will be the first Markov move. So if I freeze x2 up to xn, the linear I have to move this to the other side. The linear coefficient of x1 is a times x2 up to xn. So I have to replace x1 by a times x2 up to xn. Okay, and then I have to take away the old roots, which is x1, and then I just keep the other coordinates the same. So this is a non-linear map. This is not a linear homomorphism. This is non-linear. Okay. So I similarly have M2 up to N. It's clearly they're involutions because they're root flips. Alright. So when I was describing the automorphisms of the variety, I was just describing the complex automorphisms. Like a priori, I'm allowed to have complex polynomial maps, like the coefficients of the polynomial maps could be transcendental or something. But it just so happens, because of this classification, that all these automorphisms are defined over Z. That's like an accident, but it's true. So actually, sort of accidentally, so the automorphisms actually act on the integer points. What am I supposed to do with this? Put it off the top. Okay, so we have a non-linear group acting on a set that we want to count, which is good. Alright, so the first question is, what are the orbits of this action? So this is known like for a long time. So it was known to everybody who worked on this equation at different times. So Markoff-Hurwitz and Mordell all knew this for their versions of the equation. We're going to try to be more tidy and make 3. That the actual number of orbits is finite. Okay, so now you have this group acting on your set that you want to count, and it breaks up into finitely many orbits. So we reduce to orbital counting. Okay, so I told you something very special about the variety, so before I go on and tell you more things, let me tell you what's known about this problem. So like a historical survey. Any questions before? Alright, so whenever n is equal to 3, which is the Markov case, a lot more is known about this. So much sharper results are known. So the first theorem is due to Magee and Riven. So let n be equal to 3, a be equal to 1, and k is 0. So there exists a positive constant such that the size of this intersection okay, so you have an asymptotic formula with a very sharp error term. So it's a constant times log r squared plus O log r log r. Alright, so this is the sharpest result whenever n is equal to 3, but there was a lot of work before this. So there were previous results by Magee. So Magee's result here is only very, very slightly weaker. So what does this look like? This is a main term, and then this is essentially square root error term, square root of main term, except for this very, very small log r. So Magee in 1981, this is 1995, this is 81. Magee produced an error term which is log r log r squared. Okay, not very who cares about the difference between these. But actually, the first asymptotic formula was due to Gamburd. That's 76. Right, so at the current point in time, we don't know anything like this whenever n is equal to 4 or above. Okay, so the story starts to get pretty interesting though whenever n is bigger than 3. So the interesting part of the story goes back to 1991. So this mathematician called Bargar, who was Joe Silverman's student, noticed in his PhD thesis, 1991, that whenever n is bigger than 3, if there were to be such a result, it could not hold with 2 replaced with 3, for example. In fact, he noticed that actually if such an asymptotic formula was to hold when n is 4 or 5, the 2 will have to be replaced by a parameter which is non-integer. Okay. So Bargar first noticed this in 1991, and then he worked on it between 1991 and 1998. So I'm going to write the best result that he obtained, right, which is 1998. So let's n be at least 4. He doesn't care about what a is, as long as it's a natural number, but he needs k to be 0. And he says if there are any non-zero integer points, is non-empty. There exists a constant c greater than 0, such that I have to write my quantifiers in the right order. So there exists for each n beta, which depends on n, which is greater than 0, such that if there are any non-trivial integer points, is non-empty, then the size of this intersection that I care about is log r to the beta plus small o of 1. So this is an asymptotic formula after you take logarithms, right, but not an asymptotic formula by itself. Bargar estimated that beta of 4 is in the range 2.43, let's write this neatly, 2.48. Beta of 5 is in 2.73, 2.80, and he estimates the higher ones as well, some of the higher ones. He also proves that as n goes to infinity, beta n is asymptotic to log n on log 2. Oh, sorry. I know I'm covering this up slightly, but it's probably better to show this. So this is like the only Diophantine equation where something like this is known to happen. This is surprising to a number of theorists. Alright, so what I want to talk about today is how to improve this result to an actual asymptotic formula. But I'll also explain what beta is. Okay, so I might guess actually, but okay. So I actually want to talk about a theorem which deals with arbitrary k. This arbitrary k, there is a reason for dealing with them. They're related to character varieties. So I want to do arbitrary k, but something a bit funny happens whenever k is non-zero, which we shouldn't really worry about much, but I just want to deal with it. So if k is non-equal 0, there can be exceptional solutions. So that's like some exceptional subset of the integer points. The thing that's exceptional about them is that they have the wrong rate of growth. And they don't behave like this, not like this is poly log r. The exceptional solutions aren't poly log r, they're like linear in r. So if I have those solutions and I count them, I'm not going to see this, I'll see something more basic. I'll just give you an example. For example, whenever let's see, n is 3. Even when n is 3, these exist. A equals 1 and k is 4. You have a parametric family of solutions, which is 2tt. Right? Okay, we all see there's at least constant times, there's at least r of those less than the root of r. Okay. So we don't like those. We don't really need to worry about them. Okay. We understand exactly what they are. Okay. They're written down in parametric families. Okay.
So are you saying you want to exclude all
Yeah,
exception points and count the others?
I know what they are, I'm just going to throw them out and count the remaining ones and look for this behavior. Yeah, these are actually, okay, it sounds stupid, but these are Chebyshev polynomials, and that's not a coincidence. Alright. Okay, so I can say the main theorem now. Okay, so this is joint work with Alex Gamburd and Ryan Ronan. So Bar had this condition, which actually guarantees him that there are infinitely many things, so you can ask for an asymptotic formula. It's actually a bit more subtle in general, so we have to put that as a condition. So let n be at least 4, n can be any natural number, k can be anything. Okay, so if the non-exceptional solutions are infinite in number, then when you count the intersection after you remove them, okay, so let me add something else. There exists a constant depending on n, a, and k, bigger than 0. So the size of this intersection, removing the exceptional solutions, is constant times log r beta n plus small o of log r to the beta n.
So I suppose there's some kind of rigorous definition of exceptional solutions, or?
Yeah, so, right, I can say, so in every case we know exactly for which k they exist.
But they are all of this form?
They're all fall into like parametric curves,
Okay.
and the orbits and their own morphisms of those curves.
Okay.
Okay, so they're contained inside a countable union of curves. Well, we can explicit. I can tell you exactly what they are. Yeah. So if you don't like this exceptional thing, just let k be 0, and then they don't exist.
It's
Okay.
fine. It's fine.
Okay, I was supposed to say something more about this. So yeah, so Beauregard was Silverman's student. I want to say like an open question. So Silverman asked in the 1995 in the Columbia New York number theory seminar, like two open questions about Beauregard's results. So he asked, is it possible there is a true asymptotic formula? But he asked a more interesting question, it's still open, which is it possible that beta is non-rational? So this remains open. Okay, so we'll see in the talk that it's related to thermodynamical formalism, so maybe someone in the audience can answer that question. No, I can't.
But you wrote here bigger than infinity or 0?
It should be equal to infinity. That doesn't make any sense. Any other questions while I wait for this to dry?
You start with side.
The white one you have in your hand.
Yeah.
The other side is
Oh, I'm supposed to use this to dry it? Okay. I forgot.
Horizontally.
Horizontally is better. Okay.
These kids fast.
So in the second half of the talk, I want to explain the proof. So the strategy of the proof, that's why I mentioned Zagier's results. The strategy of the proof is to like follow Zagier's work, but sort of reinterpret it in a slightly more modern way and put it in contact with thermodynamical formalism where possible. So the proof I'm going to sketch is following Zagier's strategy. But if it was possible just to prove this theorem, just following Zagier's strategy, mutatis mutandis, then it would not be a very interesting result, okay, or paper. So when you do this, you encounter some difficulties that I'll point out. So these difficulties have an interesting solution. Okay, so we're going to follow Zagier's strategy and point out what happens. Okay, so the first phase of the proof is the very first thing you do is you think a little bit about the Diophantine equation and you realize it's sufficient to count positive integer solutions. Okay, so that's an exercise for everybody. So we first reduce to, dealing with positive integer solutions. Okay, that's okay. And then, now what we have to do is something called descent. So let me make a precise statement. There exists a compact set K. K. It lives inside R to the n, such that for all x in V of z plus minus k, so outside this compact set, something good is going to happen. And the good thing is, we know how the Markov moves affect the largest entries of tuples. Okay, that's going to be really useful. So three things happen. The first one is mostly like psychologically helpful. So I know I'm getting too low. The first one is that the largest coordinates of x occurs in a unique position. So there are two different coordinates that are both the maximal. Okay, secondly, if you do a Markov move at a coordinate which is not the largest, at non-largest coordinate, it becomes the largest. Okay, cool. So, okay. And then the last property is the same as this, but with non-largest and largest switched. So I'll write that as it becomes the non-largest. Okay, so what does this mean? It means that you look at your tuple, right, you have x, so there's some largest thing and the other ones are not the largest. That means you have n minus 1 ways of creating a new tuple with a new largest, a bigger largest entry. And you have one way of taking the largest entry and making it smaller. So one thing is descending, and n minus 1 things are going out. Yeah? So this gives you infinite descent. In particular, if you have any tuple, you can just keep applying the Markov move at the largest position and keep reducing the size of the tuple until you get down into this compact set. Okay, so this actually gives you a proof that there are finitely many orbits. Right. So Markoff-Hurwitz and Mordell all knew about this. In fact, they knew more precise versions of it. Alright, so this is really good because you're counting things with respect to the largest entry. And now you know, based on where you are in the tree of Markov moves, which one is actually the largest. But it's still kind of annoying because it could be anywhere. And I want to do some analysis, so I don't want to have that keep jumping around. So my solution to that is I'm just going to put everything in order and keep them in order. So this is like a recoding. Okay. So I'm going to think about Z1 less than or equal to Z2 less than or equal to Zn with Z as a solution. I should have also said here, I just want to make my life simple just to sketch this proof. So I don't want any exceptional solutions, and I want my formula for the Markov moves to be simple. Remember that I had A in it. Let's just put A to be 1. Okay. So let A be 1. K is 0. Okay. Just make things easy. Okay. So this is an ordered element, an ordered solution. And I want to know what the Markov moves do to ordered solutions. But I'm only going to do Markov moves that go outwards. Okay? So I'm going to do a move called, what do I call this? I think it's called lambda j. So lambda j is like a Markov move. It does Markov move and then puts things back in order. What does it do to Z1 to Zn? So it's going to do the Markov move at the jth position. That will become the largest, and then it puts them back in order. But that was the largest one, so it slides to the ends. Okay? So what happens is Zj got acted on, but then it got slid to the end, so it's now omitted. Then we get up to Z1, and now we have the new coordinate here. So this is the product over I not equal to j, Zi minus Zj. And I only want to go outwards, so I now have j between n minus 1 and 1. And I've gone from a group to a semigroup. So I want lambda to be the semigroup generated by lambda j, such as this. And I write plus for generating a semigroup. Okay, so you only allow concatenations of these things, no inverses. This is just a psychological thing, where now I know that in my tuple, the last thing is the largest one. Okay, it's just really helpful. It's not moving around anymore. So, because of infinite descent, the points with positive integer entries outside this compact set break up into a finite union of trees. Okay? But I can actually count each of those trees by counting orbits of this semigroup. This is some technical thing you have to check. What I'm persuading you is that I've actually reduced my counting problem to counting under orbits of this semigroup. So we've reduced to the question of what is the size of an orbit, lambda.o, intersect VR.
Can you remind me again why you have finitely many orbits? What's that argument?
Well, you can always descend, right? So you're descending, but then you get into a compact set, but it's like integer points in the compact set, so there's finitely many of those. So the outcome of descending is like finitely many possibilities.
Oh, okay.
Yeah, it's compactness plus integer points.
Okay.
Okay, so that's phase 1, which is basically just setting up some kind of coding that you like. It's descending. Phase 2 is, okay, so where are we at now? We're doing orbital counting for a non-linear semigroup, which is actually sounds pretty hard. So phase 2 is to reduce the problem to something you know how to do, which is linearization. Okay, so you want to linearize this problem. Okay, so I'm going to actually do a little bit of analysis, okay, here. So I'm going to make some statements whose quality depends on a certain quantity. Okay, so let me introduce some quantity. It'll be useful in my analytic statements. So let alpha of z be equal to the product of I less than or equal to n minus 2 z I. Yeah, I'm sorry if you can't see the bottom of this.
Can't do much better than switch them. Yes. Switch them now.
Switch them now? Maybe. So what I'm saying is like the product of the n minus 2 largest entries is going to be important. Okay? So I'll tell you why. So there are two statements. Oh, this is hard to reach. So A. I already have A. Forget about these.
E prime.
How am I going to linearize? I'm going to do something really like coarse, which is I'm going to take logarithms. Okay? When I say I take a log of the vector, I take a log of all the entries of the vector. Yeah?
Just when you say trees, are you saying that lambda is a free semigroup?
Lambda is a free semigroup of polynomial maps, yeah. And it acts freely outside the complex set. That's all. Okay, the first thing, so I'm going to take logarithms and see what happens. So I'm going to take log of z. The first observation is when you take log, you land close to a hyperplane. So, okay, so how do I say this? So, okay, just the log of z is close to, so approximately in, a hyperplane. I should say actually just, it's alpha, not this chalk is disintegrating, alpha of z inverse close to a hyperplane. Okay, so this statement improves whenever alpha of z gets big, where the hyperplane is given by the collection of y1 to yn, such that the sum y is 1 to m minus 1 yi equals yn. The second statement is about what happens, what do the lambda j's look like when you take logarithms. So the picture is that I have a z, and I apply lambda j, and I get lambda jz. But then I can also take log of z. And I can also take log of this. Okay, so if I know that this is close to on the scale of alpha z minus 2, so point y in h, then this is actually close to, on the scale of alpha z to the minus 2, some linear transformation of y. Okay, so this now seems a bit abstract, like I'm doing category theory or something, but okay, what's actually going on? What I'm saying is, if alpha of z is large, it allows you to neglect this zj here. Okay? So whenever you take that away and take logarithms, that product becomes a sum. So this is going to be close to something called gamma j of y. Okay. Let me move this up. Where gamma j of y is like the linearization of this thing. So it's gamma j of y1, yn is y1, yj hat up to yn, and then sum from I not equal to j, yi. So you can think of this as like, when you take logarithms, the lambda orbit's getting tracked by a linear orbit. Okay, it's getting tracked closely. So I can point out the first problem, which is that what I basically want to do in the proof is like bootstrap up to a scenario where alpha is large, so that I can use that. The problem is, it's actually possible to go to infinity in the orbit without alpha actually changing at all. The way to see that is that lambda m minus 1 doesn't actually change the first m minus 2 coordinates. Okay, so why is that not a problem for Zaghier? It's not a problem for Zaghier because Zaghier has something better than just taking logarithms. He has a function that's related to hyperbolic geometry. It involves Markoff, okay, but he has a more precise function, and his function has the property that this stuff works as long as any coordinate is large. So here we're doing something more coarse, so we have a problem because of it. basically done what we wanted to do. Let's just use the other part of this. So we've managed to compare lambda orbits to orbits of a linear semigroup. So we're now in a situation where probably like most people here can actually solve, like do the counting. And everyone has their own preference for how you deal with this. So let me explain what we use. So part 3 is that we've reduced to the question of, okay, let gamma be the semigroup generated by these linear things. This is a linear semigroup. So we reduced to counting the size of an orbit under gamma, x naught, intersect the Paul radius log r. Alright, so how do you do linear semigroup counting? This is a free linear semigroup. I should also say that this semigroup preserves that hyperplane. So this is a linear semigroup acting on a hyperplane. We want to count in orbits. The way I like to do it is by renewal method. So we use Lally's renewal equation. I'm not going to speak for very long about this because I want to get to the punchline of this talk. But basically the idea of renewal is that you have a free semigroup, so you're counting over a tree, but you're not counting with respect to like the word length in the tree, you're counting with respect to some other counting parameter. But because you have a tree, you still have a recursion. Okay? You always have a recursion on the tree. So it's this recursion that gives you the renewal equation. And taking the Laplace transform of the renewal equation gives you a transfer operator. This is one of the big ideas in our paper, which is that Lally's original version of this was for hyperbolic space, and counting in hyperbolic space. And what he does is he compares the orbital count to the boundary of hyperbolic space. But there's no obvious boundary here. We're not in a symmetric space. So the idea of the paper is instead of using the boundary of hyperbolic space, we use the projectivization of this hyperplane. And we can make this work. So we need to study the projectivization of this hyperplane, which I'll call delta. This is like the boundary of hyperbolic space. Okay. And we study a transfer operator on this, what do I want to say about this? Okay, so we need to study the action of this semigroup on this projectivization. So this is acting projective linearly. And we study a transfer operator, which is LS, which goes from C1 of this thing to C1. So LS of Fx is sum from I is 1 to n minus 1, e to the minus s tau, gamma I x, f of gamma I x. If I wrote that correctly, it's a miracle. So the thing is, what is tau here? What's the potential? I have like 5 minutes. What's the potential? Well, the potential is actually dictated by the renewal method. So the potential you have to use in the transfer operator, it comes from the counting problem, like you don't get to choose it. But there's a funny thing here, which is that the way we were counting before, the potential here, the tau, it ends up being log Jacobian, which is something familiar. So tau is log Jacobian. Okay. So let me just finish by like drawing a picture. So let's draw the picture whenever n is equal to 4. And we'll see what the difference is between n is 3 and n is 4. Okay, so here's what it looks. The projectivization is 2-dimensional, because there were 4 dimensions. You went to a hyperplane, you lost 1 dimension, then you projectivized, so you lost another one. It's a simplex, it's a triangle. So this whole triangle is delta. And let me draw this picture correctly, which I can sometimes do. I did practice this. Okay. No. Very good. Oh, it's like this. Okay. So this is where gamma 1 maps delta. This is where gamma 2 maps delta. And this is where gamma 3 maps delta. Nothing maps here. So there's a hole. By the way, the n equals 3 picture is just what's happening in this segment. There's no hole. So what happens when you propagate, you do more and more gammas? That hole shows up, the copies of that hole show up in other places. Okay, more and more copies. And eventually you remove something of the big measure 1. So this thing actually, this has a fractal attractor. When n is greater than or equal to 4. When n is equal to 4, okay, so we discovered this thing in our paper, okay, we thought this is amazing, we found this thing, but when you find something so amazing, normally someone else finds it first, okay, so we did not discover this thing. When n is 4, this thing is essentially the Rauzy gasket. This was studied by many people before us. I'm going to write their names, so Levitt, DeLeo, Dinikov, Arnaud, and Storostin. Okay, and also Avila, Skripchenko. These are not in the right order, but Hubert. And maybe other people in the audience, if I haven't written your name and you should be here, I'm sorry. No, seriously, I tried to find everything. The amazing thing about Avila, Skripchenko, and Hubert is that they not only studied this Rauzy gasket, they actually did the thermodynamical formalism for it. They didn't do everything we needed. We didn't know about the result when we wrote the paper, but there's a significant overlap between what they'd done and what we did. Alright, I just want to finish on time, so what have I got left to say? Let's just finish by saying what is beta. Beta is 0 as a pressure function. I want to say it correctly. Beta is n minus 1 times the 0 of pressure. Okay, I'll stop here. Thank you.
Thanks, Michael. Beautiful talk. Questions?
There is one way to get, which is like not as good as the first one you mentioned of machine reading, is because of the linearization or because of the formalism that is not good enough to
The reason we don't get something like machine reading. Oh, okay, so that's a really great question. So there are two open problems that I'd like to advertise, which are related. So the first step is prove that the invariant measure is a doubling measure. Secondly, prove the Gopian estimates for this. Okay, and then if you can do these two things, I think you need to do the first one to do the second one. If you can do these two things, you can, in the error term, instead of writing small o, you can write log r to the beta minus epsilon for epsilon greater than 0, which would be very nice. But it's quite a complicated system, so it's not conformal. Yeah, it's on the edge of what people can do, or maybe slightly beyond.
Well, I might have one. So, in what context did Pierre Arnoux come to this one? I mean, he normally works on substitution systems, so does he have an iterated function system that comes out of a tiling system to get that?
I don't know this stuff very well, but it's some generalization between fractions, like Fibonacci fractions or something.
Oh, okay.
I think
Yeah, that's a substitution system. You see it this
Yeah.
Other questions?
Is the beta exponent in your theorem related to like Hausdorff dimension or some?
Is the beta?
Yeah, as you guys.
There's a conjecture, but there's a conjecture of an inequality, but it's not the same.
It's
Okay,
not-
the basic answer is like it's not the same because the dynamics is not conformal. Okay. So there are different Lyapunov exponents. When I say not the same, not an obvious multiple. Yeah. There's a conjecture of delay on a relationship between the Hausdorff dimension and beta. Let's see. Like the Hausdorff dimension should be bigger than or equal to 2/3 beta whenever n is 4, something like this. I may be saying it not right, but.
Any other question? Well, if not, then let's thank Michael again.